So what I want to talk about today is Long Island and the landscapes of Long Island. Long Island has a variety of interesting and unusual landscapes. And I'm a geologist, and geologists are interested in explaining how things came to be the way they are. We're interested in origins, and we're interested in the materials that make up landscapes, and we're interested in the processes that make up landscapes. And if you live on Long Island, you kind of take it for granted, you know, this is the way the world is. But it's actually a really interesting and unusual place. And when you're wondering about explaining the landscapes on Long Island, there's really one key to the whole thing, and that's ice. Remember Vanilla Ice? Long Island is a product of ice. It is landscapes that were brought to us courtesy of glaciers. And I'm standing, in this photo, I'm standing on a glacier up in British Columbia called the Athabasca Glacier. Big tongue of ice, or river of ice, if you will, that comes down out of the Columbia ice fields and works its way down the valley. To the point where it melts. And the thing to understand about glaciers is that they are constantly in motion. They are rivers of ice that are continuously sculpting the landscape, but also building the landscape. So glaciers are destructional, but they're also constructional. And the constructional activity primarily happens at the margin of the glacier, where as the ice is melting, it's dumping all kinds of material and building up a landscape. And Long Island is the product of a glacial ice margin and the building up process primarily. So if you want to understand Long Island, you need to go study glaciers and see, well, what are the kinds of features that they build, what are the kinds of materials that glaciers produce. And in the photo here, you can see one of the main products of the depositional activity of glaciers at an ice margin are these ridges of bouldery sediment, which are called moraines. And here's a view of the terminal moraine of the Athabasca Glacier, the farthest one away from the front of the ice, where they cut a road through it. And you can see it's just this jumbled pile of material. So if you visit a glacier, and I encourage everybody to get to see one before they all melt away completely, what you will notice is that there's just a tremendous amount of material being melted out of the ice. Glaciers are incredibly dirty things. They pick up all this rock and sediment, they carry it, and then they release it onto the landscape. So you see, you know, the meltwater exiting the glacier is milky and full of sediment of various sizes. Along the margins of the ice, you see just a tremendous amount of debris, rocky debris of all sizes being released from the ice. You notice tunnels inside the ice where meltwater is flowing. You see meltwater disappearing into the ice. You see meltwater emerging from the ice. And you see things like this. I was fascinated by these piles of sediment sitting parked. It looked like somebody drove a dump truck up onto the ice and just offloaded a bunch of sand, gravel, and cobbles. How does something like that get there? Well, at some point, the ice was higher before it melted away, and you had some depressions, and meltwater flowing into those depressions was depositing rock and sedimentary material. And then as the ice melts away, that hole full of material ends up a pile of material on the surface of the ice, and eventually, as the ice melts away completely, that'll be a pile or a couple piles of material on the ground. So, very important idea here, which is that there's this inversion that goes on. When you go from the glacier to the deglaciated landscape after the ice melts away, everything that's positive in the form of ice becomes a negative on the landscape, and anything that's a negative in the ice, any tunnel or cavity in the ice becomes a positive on the landscape. Because of all of this sedimentary material, rocky material that fills in all of the negative spaces in the ice to become positive spaces on land. So on the landscape. So here's a cartoon showing the margin of a large glacier, and what are some of the things that are going on here? Well, you have tunnels under the ice where meltwater is working its way along the base of the glacier and exiting out the front of the glacier and depositing lots of material along the margin of the ice. You have blocks of ice which have been, fallen off the front of the glacier as it's melting and become stranded and buried in this outwash material. You can have lakes forming at the margin of the glacier where meltwater becomes impounded behind older moraines or lobes of ice. The ice doesn't melt back completely evenly. Some parts melt faster than others, so you can get embayments in the ice that trap water. Sediment being deposited into one of these proglacial lakes will build a delta out into the lake, and then as the ice margin shifts back, the lake will drain away. And again, the sort of negative becomes a positive on the landscape. All right, so if we get rid of the ice, what we're left with are lots of landscape features, such as a relatively flat and elevated outwash plain built up layer after layer by all of the material being washed out from under the ice. Remnants of the tunnels that were supplying or channeling meltwater to the front of the ice. And it turns out that ice tunnels, if there's solid bedrock beneath the ice tunnels, then you will leave behind a kind of a sinuous hill, which is all the sedimentary material that was deposited within the tunnel left sitting on the landscape. But in the case of Long Island, where we didn't have solid bedrock beneath the ice, we had relatively unconsolidated to semi-consolidated sedimentary material. Where you have ice tunnels, you actually erode down into the material below the ice to form something called a tunnel valley, and I'll show you some examples of that. That delta that built out into the lake, once the lake is gone, becomes a fairly large hill called a came delta. And then meltwater flowing across the outwash plain will erode very wide and relatively shallow meltwater channels. So these are the kinds of things that we associate with the margin of a glacier, and we can look for these features in the landscape of Long Island, and not surprisingly, they're all over the place. So let's go from cartoon to image. This is a deglaciated valley in Alaska, and so the ice margin used to be somewhere around here. The glacier retreated, and you can see what's left behind. You have this very, very irregular, bumpy landscape, which is caused by all the rocky material in the ice just melting directly out of the ice as the glacier. I mean, glaciers don't really back up. They're not like they're not like pickup trucks. They don't roll forward and then you put them in reverse and they back up. They back up by just wasting away, by melting away. And when that happens, if it happens fairly rapidly, the ice just dumps whatever it had in it, and you get this very irregular sort of landscape. And then this thing here, which is kind of lobate, that's a delta. So that was built out into standing water when there was some kind of proglacial lake here, probably held in by these hills and a lobe of the ice over here. And then the lighter colored smooth material, that's the outwash. That's the well-sorted, probably mostly sandy material that was carried by flowing meltwater out from under the front of the ice. And then also we have lots of depressions where there were blocks of ice that were getting buried in the glacial material, and then finally those ice blocks melt away, and you're left with these bowl-shaped depressions, which are called kettles. The bumpy hills that are left behind by pockets of material that were collecting in the ice that get left on the ground are called kames. So geologists speak of kame and kettle topography. sort of knobs and depressions, knobs and depressions. So I want to show you a quick video here that was done by the Maritime Museum up in Norwalk. It's probably the best video for just visualizing how Long Island formed. It's mostly wrong, but so what? You know? No biggie. The truth is we don't really know exactly the sequence of events that went into the formation of Long Island.
Is that Yosemite?
I'm sorry?
Is that Yosemite?
That is Yosemite, yes. And you know what? It occurs to me that, hold on one second here. This is not going to work unless, you know what? I'm going to skip the video because I can't get it to show on the right screen here, but that's all right. I'll just tell you what you missed. I don't want to eat up time with this. So what the video shows is the ice coming down, right, coming across New England and parking itself about midway across Long Island, sitting there for a little while. So the ice comes down about 30,000 years ago, parks, deposits a line of hills that forms a moraine that extends out to the South Fork here, retreats, parks about 20,000 years ago, deposits another line of hills, which becomes the North Fork, and then backs up completely, melts back up into Canada, and that's, you know, that process goes from about 20,000 or 18,000 to about 15, 12,000 years ago. What's wrong about that scenario is that, as far as we can tell, the movement of the ice was, it didn't advance, pause, retreat, pause, and then retreat again. It moved back and forth a couple of different times, and there seems to have been one last major re-advancement of the ice that impacted western Long Island more than eastern Long Island. And it's also pretty clear that the ice made it probably farther south than the southern extent of Long Island. All right, so let's start with the big features of Long Island. If you look at the geomorphology of Long Island, there are basically four or five features that stand out very clearly. A distinct ridge of material that runs along western Long Island, but has hilly, bumpy, valleyed terrain to the north, forming the necks of western Long Island. A similar ridge, not quite as sharp, that runs right along the coast, along the northeastern half of Long Island. A ridge of material that runs across the center of Long Island out to the South Fork, which is interrupted on the sort of Nassau-Suffolk border by these large kind of lobes of material that form hills. All right, so to put some names on these things, we call this ridge the Harbor Hill Moraine. The other ridge that's a continuation of it, the Roanoke Point Moraine. The Ronkonkoma Moraine is the southern ridge. These large sort of lobate hills are almost certainly came deltas. They are large deposits of material that built out into a standing body of water, a proglacial lake. Now, it's not really clear what was causing that lake to form, what the dam was. It's possible there was an embayment in the ice here. It's also possible that there was a moraine further to the south, now offshore, that allowed a proglacial lake to form. We know that ice advanced further south than the Ronkonkoma moraine because we can find glacial erratics buried in the southern part of Long Island. All right, so there is some glacial material that melted directly out of ice further south here. But whatever moraine is down there has long since been eroded away by the Atlantic Ocean. In terms of material, glaciers deposit basically three types of material. They deposit this stuff called till, and this is a photograph of the shoreline along Comset State Park, and you can see in the cliff here a good example of glacial till. It's not layered. It's a massive deposit of material that, oops, go back, has a wide variety of different particle sizes. Everything from big boulders, glacial erratics, to gravel, cobbles, gravel, pebbles, sand, silt, and clay. So it's very, very unsorted. It's just a jumble of all particle sizes. The reason it's all particle sizes is because it was carried by ice, and ice picks up everything, doesn't discriminate, and then it melted directly out of the ice. So glacial till, we call that an ice contact deposit. It is deposited in contact with ice. Up at the top here, there's about a foot of material that's almost like powder, very, very fine material, which is called loess. And loess is ground up rock fragments that are produced by the ice flowing along a bedrock surface, and then released when the ice melts. This material is released and it dries out. It's picked up by the wind, and it's deposited when the wind finally slows down, and often forms relatively thick soil layers at the surface. And the thing about loess is it's very nutrient rich because it's full of sort of pulverized mineral that has not chemically weathered, hasn't chemically degraded. So a lot of trace nutrients, mineral nutrients, are found in loess. It makes for really, really good soils. And the loess deposits on Long Island didn't form when the ice was here. They formed after the ice had retreated back up into New England, when the valley where Long Island Sound is was a large dry valley full of glacial deposits, and the wind sweeping down from the north picked up this very, very fine material and blew it southward. And then when those winds hit the moraines on Long Island and slowed down, this material was deposited across Long Island, but it wasn't deposited evenly. There are some parts of Long Island that have lots of loess, and other parts of Long Island where the loess was swept away elsewhere. So we have glacial till, we have loess, and then we have what's called stratified drift or glacial outwash. So if you see any layered material, like you see in the cliffs at Comset here, you know that material was deposited by water that was flowing out from under the ice. Here's a close-up. So in this case here, you have layers of sand and gravel. Some outwash is gravelly, some outwash is a mix of sand and gravel, and some outwash is just sand. It really depends on how far away you are from the ice. The further away from the ice the material is transported, the more fine it tends to become, and the better sorted it tends to become. And don't want to get much further without mentioning these enormous chunks of rock, these big boulders that the ice picks up, transports, and then releases when it melts. These are called glacial erratics. Erratic comes from the Greek. It means to wander. So these are wandering boulders, accidental tourists, essentially, brought down from either New England or from the bedrock that's now sitting under Long Island Sound and deposited on Long Island. It turns out that most erratics don't come from very far away, especially the big ones. So they tend to, being transported in the ice, they tend to break apart. So a big boulder will break into two halves, and then those halves will break into quarters, et cetera, et cetera. And really, really big glacial erratics like this tend to be fairly angular. And again, that tells you that they haven't been transported very far. They tend to become more rounded the longer they travel. So most glacial erratics probably most really big glacial erratics like this one probably only traveled less than 10 miles from where they were plucked from the bedrock to where they were deposited. It also turns out that most large glacial erratics are sitting on the surface rather than being buried in the glacial deposits. And so it looks like it was the last sort of final advance of the glacier riding up over previously deposited glacial deposits that brought the big boulders, and then the ice wasted away and left them sitting behind. There's a geologist named Herb Mills who works for Nassau County, and he's done some really interesting work showing that, that the older glacial deposits on Long Island are made up of smaller boulders, and it's the youngest glacial deposits that have the biggest boulders, and he thinks that's because with each advance of the glaciers, you were sort of eroding down through the weathered bedrock, and finally, by the time of the last glacial advance, the glacier was riding over a really fresh bedrock surface and plucking up large chunks of unweathered bedrock. All right, so let's look at some features on Long Island. I already talked about these lobate things, which I think you have to conclude that they're came deltas, that they're deltas that built out into some kind of periglacial lake, and then when the lake drained away, they were left as hills. They look like deltas. They have that kind of bird foot shape. They're very, very lobate, which you get the lobate shape from distributary streams flowing off in different directions and carrying sand and gravel and depositing that material into a standing body of water. So these don't look a whole lot different from, say, the Mississippi River Delta building out into the Gulf of Mexico. And there's a large one here, there's one here, and looks like the end of one here, which has been chopped off by the Harbor Hill moraine. And then these things seem to cut across the Ronkonkoma moraine, which suggests that they formed after the Ronkonkoma moraine formed. So it's very difficult to date glacial deposits. There usually isn't much in them that's datable. And if you can find, even if you can find some organic material, radiocarbon dating only works going at most 80,000 years. So there's a limit to how far back you can date things using, pieces of wood or whatever organic material you can find. So we're not, we're not really able to precisely date these features, but we can at least tell which came first and which came later. And it seems pretty clear that the Ronkonkoma moraine was there, and then these things were kind of deposited through it. With maybe not this one, but certainly these cut across it. And then the Harbor Hill moraine is the last feature. It comes along and it truncates the Ronkonkoma moraine, and it truncates these came delta features here. And the Harbor Hill moraine is almost certainly the youngest glacial event on Long Island, where the ice made one last sort of major re-advance and kind of bulldozed its way down, creating this very, very sharp ridge. And in the glacial deposits in the ridge of the Harbor Hill moraine, you can often find the layers folded and pushed up against themselves, which means that they were literally kind of bulldozed. We call that ice thrusting. The ice pushed forward and bulldozed up the deposits that it had deposited previously. And then you can see very nicely here how these smooth areas, the outwash plain, so all the sediment that being washed out from under the ice was being deposited in front of the moraine down here, and you can see how the came deltas are kind of buried in this outwash material, that they were sort of in the process of being buried in the younger material that was being deposited. You can especially see it over here. The edges of these hills look like they're partially buried in these smooth deposits. And then we have all these valleys, and these valleys were the conduits for the meltwater coming out from under the glacier. So brings us to kind of the next topic, which is this very interesting topography along northwestern Long Island, the necks of western Long Island, and these bays, these very, very narrow, very deep harbors that we have. Completely absent from the eastern part of Long Island. However, if you look at the submarine topography, you can see the remnants of necks here. So eastern Long Island used to have necks, but they've been eroded away by the wave action coming off of Long Island Sound over here to the east, where you have the opening to the open Atlantic. So there's more wave energy impacting eastern Long Island, and so the necks have been eroded away here. They're in the process of being eroded away here. They're still present here because there's so much less wave activity. There's also much less fetch for wind to blow across in the western Long Island Sound, so the waves tend to have less power, so they haven't done as much erosion. So these necks and bays are pretty unusual features. Turns out they're not really that unusual. If you look at other regions of the United States that hosted glaciers at the end of the last ice age, you can find similar features. So this is the Sturgis moraine, which is sort of right on the border of Indiana and Michigan. And this is a digital elevation model, so the blue is not water. The blue is simply lower elevation. Green is mid-elevation, and then the yellows and oranges and reds are the high elevations. And what you see here this is a terminal moraine. So you see this very bumpy, hilly morainal surface, and then these valleys that cut through the moraine, and these are meltwater carved valleys. So the edge of the ice was here. There's the smooth, kind of built up outwash plain that piles up in the front of the glacier. And these were tunnels beneath the ice where meltwater was flowing out to the front of the ice and then disgorging to deposit the outwash fan. Looks just like the necks of western Long Island because it's the same feature. So along at the margin of the ice, you have all this meltwater coming up from under the ice and carving or eroding down into the subsurface. If you don't have solid bedrock, if you have older glacial material or coastal plain material, semi-consolidated sands and gravels as we have under Long Island, you're going to erode down into that stuff, and then all the sediment gets disgorged at the front of the ice, and it builds up an elevated area. So where the ice was, it's lower. Where the ice wasn't, it's higher. Here's another graphic that just kind of demonstrates that. So meltwater flowing up under the ice and over the ice builds up this outwash plain. If we look at some examples, this is, all right, so this is the Huntington Northport area, and you see lots and lots of tunnel valleys. The tunnel valleys tend to trend north-south, and most of the meltwater was flowing towards the margin of the glacier. But you can also have tunnel valleys that trend east-west, and they sort of branch. Tunnel valleys can go up and then down again because the water is flowing under pressure, so it can flow uphill because it's under pressure and then flow back downhill again. So here's a tunnel valley that starts out at sea level, rises, and then drops back down to sea level. If we look at some profiles from Lloyd Neck down to South Huntington here, you can see that the land is lower where the ice was, and it got built up in this outwash plain where the ice wasn't from all this material being transported. Same thing in the Northport area where the ice was. The land is lower, crisscrossed by all these tunnel valleys, and then built up to form a nice elevated outwash plain to the south. Here's a digital elevation model of the Northport, East Northport, Kings Park area. And there's the crest of the Harbor Hill moraine, the tunnel valleys, and the outwash plain. Notice that Northport Harbor and Centerport Harbor combine. They're a split tunnel valley that combines into a single valley, goes up to the crest of the moraine, and then you can see there's this broad kind of channel. Here's another outwash, another tunnel valley that was disgorging through the moraine and depositing material, and you can see an outwash channel here that got buried in the outwash coming out of this channel. So there are the major tunnel valleys and conduits for meltwater in the Northport area. That outwash fan that builds out and buries an older tunnel valley, or an older outwash channel coming from a tunnel valley. And not surprisingly, most of the roads follow these tunnel valleys. They're sort of natural pathways. So if you're familiar with the Northport area, if you drive down Bread and Cheese Hollow Road, you're driving down through a tunnel valley. Waterside Road is a beautiful example of a tunnel valley, very steep sides as it winds down. Main Street in Northport is also a tunnel valley branch. All the valleys on the North Shore are tunnel valleys. And they don't have streams. These are not stream valleys. There's no flowing water. These valleys were not carved by streams. They were carved by meltwater flowing under a continental glacier. It's kind of mind-boggling to think about. Port Jefferson's another beautiful example of a tunnel valley, and then a very, very broad fan-shaped deposit of outwash south of the crest of the moraine. All right, what about rivers, lakes, and ponds on Long Island? Rivers, lakes, and ponds on Long Island are the products of glacial deposition and glacial erosion. With one exception, really, and that's the Peconic River. The Peconic River is a normal river. It occupies a drainage basin between the Ronkonkoma Moraine and the Harbor Hill Moraine. Precipitation falling within that drainage basin is fed as groundwater into the Peconic drainage, and it exits into the bay. Perfectly normal river. But the Carmen's River, the Connequot River, the Nissequogue River, these are all what we call underfit streams. They are wimpy little rivers occupying much broader valleys that they did not carve. So these rivers are occupying large meltwater channels connected to what were probably tunnel valleys. So when the margin of the ice was down here, you had tunnel valleys forming from meltwater flowing under the ice. And this is almost certainly a tunnel valley feature here. And the path of the Nissequogue River is probably following a tunnel valley, probably. If we look at central Long Island, there's Lake Ronkonkoma. Lake Ronkonkoma is a big depression left behind by a giant block of ice that got buried in the moraine. When the ice finally melts away, it leaves a hole that's deep enough that it intersects the water table, so you have a lake. There's the Nissequogue River up here, occupying what's probably an old tunnel valley. The Connequot River occupying a meltwater channel. Here's an old meltwater channel. This may have formed when a proglacial lake impounded behind the Ronkonkoma moraine was able to breach the moraine and drain out to the south here. Most of the rest of the valleys that we see on Long Island are what we call dry valleys, because there's no stream in the upper reach of the valley. It's only in the lower reach of the valley do you have water. Dry valleys are really interesting things. How do you erode a dry valley? Well, you need water to erode. I mean, you're south of the glacial moraine, so it wasn't meltwater that carved these valleys. They're not connected to the glacier. So there must have been flowing surface water that eroded them. But the problem is that the water table's too low. And back, during deglaciation, the water table would have been even lower than it is today because sea level was much lower at the time. So these dry valleys are a bit of a puzzle to explain, but there's an interesting clue. This is the Bridgehampton area, and you can see there's a valley here, runs along here, that intersects a pond. And how do you do that? How do you erode a valley through a pond? It's pretty much impossible. Here's a digital elevation view of it. So we got a couple branches of this dry valley here. which cut right across this string of kettle ponds. Turns out that you can explain this if you think about the fact that when these valleys were eroded, Long Island was a permafrost region. So you had permafrost, so the glacier retreats, but it's still cold, so you have this permafrost, and the permafrost forms a perched water table that then allows you to, allows water to collect on the surface and start to erode these valleys. The ponds are not yet ponds yet. They're buried blocks of ice. So the streams are flowing across ice, right? And eroding down into the landscape and into the ice. And eventually the ice melts away and you're left with depressions. But you've already formed the dry valley, so it's already there by the time you have a depression. So most of the south-flowing streams in southern Long Island are dry in their upper extent, but only have water in their lower extent where they intersect the modern water table. And all of these southern-flowing small streams were almost certainly eroded after the ice retreated, but when the region was still the ground was still permafrost. A few other things in my last couple minutes here. The came and kettle topography of the moraines is very well developed all over Long Island. The Northport area is a good place to see it. There are some nature preserves up in Northport where if you hike around, you see these sort of bowl-shaped depressions. These are kettle depressions, but they're above the water table, so they're not ponds. You see glacial erratics all over the place. It's a very bumpy, very steep, hilly topography. Got to be careful, some of those glacial erratics. Dangerous. Out on the South Fork, a beautiful came and kettle topography associated with the Ronkonkoma moraine and the ground moraine north of the Ronkonkoma moraine. Again, by now you should be recognizing these things. These tunnel valleys where meltwater was flowing up to the front of the ice, and then the meltwater channels associated with the tunnel valley. So you see this sort of triangular valley that then opens out into another shallow triangular valley. So the meltwater tunnel, and then the outwash channel. And then again, this very, very bumpy, irregular topography, these deposits of came hills and the kettle depressions in between them. I've never tried this, but I imagine if I took a cooler full of ice cubes and mixed it with sand and then dumped it on the ground and let the ice cubes just melt away, this is kind of what you'd be left with. Lots of kettle ponds on Long Island, mostly in eastern Long Island and western Long Island. We've filled them in, developed them. A couple big ones, Lake Success, Lake Ronkonkoma, of course, very large kettle depression. Up in northern Suffolk County, bunch of kettle lakes that are, again, they're in the lower part of the outwash plain, so they're deep depressions and they intersect the water table, so they're ponds. And then out on the South Fork, they tend to come in strings, and we don't really understand why exactly, but there tend to be these chains of kettle lakes. So somehow you were leaving behind chains of blocks of ice. Sometimes they're associated with meltwater channels. Notice here that the depressions continue across the moraine. They're just not flooded because they're too high. Here's a chain of depressions occupying a chain of kettles occupying a meltwater channel, but here's a chain of kettles that isn't associated with a meltwater channel. And I don't think we really understand exactly how these things were forming. And then finally, in my last minute here, the Hempstead Plains, that occupies the outwash plain, so a broad area of sandy outwash soil, but with loess mixed in, so it's a relatively nutrient-rich soil. But the Pine Barrens, for whatever reason, the prevailing winds seem to have swept away most of the loess from this region, leaving behind a sandy soil which is very nutrient poor, and that sets up the ecology of the Pine Barrens. If we look at sort of the different forest types on Long Island, the pine, the pitch pine, shortleaf pine ecosystem seems to like the outwash. We have this very, very sandy material, but also occurs in the moraine. And the one thing I just want to point out is that there's a mosaic of different communities occupying the moraine, because there's a mosaic of different sediment types. You can have glacial till in one area, and then adjacent to it you can have glacial outwash. So it's a very patchy substrate associated with these glacial moraine deposits. All right, and then I just want to thank or acknowledge really the people who've done most of this research. Gil Hansen and his students at Stony Brook have really just greatly expanded our understanding of the glacial history of Long Island. Les Serkin, who passed away quite a number of years ago now, was sort of the deacon of glacial geology on Long Island for quite a while. Herb Mills at Nassau County Museum, who continues to do really, really interesting work on the glacial deposits of Long Island. And then my colleague, Charles McGarrian at Hofstra, who's a person who kind of got me into this. Thank you very much.